Good morning, dear students. In the last session, we have studied about the group 15 elements, general characteristics, chemical reactivity, and then about nitrogen element. We have studied about the preparation, properties and uses of nitrogen. And in this session, we will study about two compounds, their preparation, properties and uses at the beginning. So, to start with ammonia. So, ammonia is one of the very important compound used in industries, mainly in the preparation of fertilizers. So, how do we get or prepare ammonia? ಸಾಮಾನ್ಯವಾಗಿ ಈ ದನದ ಕೊಟ್ಟಿಗೆಯ ಹತ್ತಿರ ಹೋದಾಗ ಅಥವಾ ಸಾರ್ವಜನಿಕ ಶೌಚಾಲಯಗಳು ತುಂಬ ಜನ ಹೋಗಿ ಯೂಸ್ ಮಾಡುವಂತಹ ಶೌಚಾಲಯಗಳ ಸಮೀಪ ಹೋದಾಗ ಒಂದು ರೀತಿಯ ಡಿಫ್ರೆಂಟ್ ಆದ ಸ್ಮೆಲ್ಲನ್ನು ಬೀಯಿಂಗ್ ಕೆಮಿಸ್ಟ್ರಿ ಸ್ಟೂಡೆಂಟ್ಸ್ ನಾವು ಅಬ್ಸರ್ವ್ ಮಾಡ್ಬೋದು. ಅದಕ್ಕೆ ಅಮೋನಿಯಾ ಕಾರಣ. ಸೊ ಅಮೋನಿಯಾ ಈಸ್ ಪ್ರೆಸೆಂಟ್ ಇನ್ ಟ್ರೇಸ್ ಕ್ವಾಂಟಿಟೀಸ್ ಇನ್ ದ ಏರ್ formed by the bacterial decomposition of organic matters. So bacterial decomposition of organic matter in air also produces ammonia in trace quantities. For example, urea. If you consider NH2CO, NH2, this is urea. First it gives ammonium carbonate which decomposes to give ammonia. So, urea decomposes and produces ammonia. This is the smell. Now, this is in air. Then how do we prepare this ammonia in the laboratory? Try to recall the first year salt analysis which I have done, where you have gone for a zero group basic radical, detection of ammonium radical, where you have taken an ammonium salt like ammonium chloride or ammonium bromide, add a base like sodium hydroxide, or you can add the other bases like calcium hydroxide, potassium hydroxide. You got a pungent smelling gas that is exactly ammonia, which you have already prepared in the first year practical. So, we will see the preparation in the laboratory by treating ammonium salts like ammonium chloride or ammonium sulfate or ammonium nitrate, any salt with sodium hydroxide, bases like sodium hydroxide or even calcium hydroxide can be used to give ammonia so ammonium chloride and calcium hydroxide react to give ammonia gas, which is a pungent smelling gas. Or you can use ammonium sulfate and add sodium hydroxide, which also gives ammonia gas. So ammonium plus water. So, ammonium sulfate when reacts with sodium hydroxide also gives gaseous ammonia. This is you are doing in the second year also, you are going to do it in the detection of ammonium radical in the zero group, the pungent smelling gas ammonia. Then what is very important in view of your examination is the next one which I am going to discuss now, the manufacture of ammonia. scientists together, one Haber and Bosch, prepared it in the early 20 decade. So, manufacture of ammonia from nitrogen and hydrogen, which I have seen in nitrogen. Nitrogen, when reacts with hydrogen, it gives ammonia with the liberation of 46.1 kilojoules per mole of heat. The two scientists got Nobel Prize for this method of manufacture of ammonia, and that is why called as Haber-Bosch process or Haber's process. This method is important for industries and for your examination. Normally from inorganic chemistry, this question comes in the annual examination. So, Haber's process of manufacture of ammonia. So, nitrogen and hydrogen react in 1:3 ratio by volume to give 2 volume of ammonia, and you can observe the sign in between the reactants and the products. This is reversible, and after you start the reaction, there is attainment of equilibrium. So, about equilibrium you have studied in the first year. Once the equilibrium is reached, the concentrations are constant, then how reversible reaction is also proceeding here, then how do I get ammonia in maximum amount, or how do I increase the amount of ammonia, or I have to favor this reaction in the forward direction. So, forward reaction, if you favor the equilibrium, more amount of ammonia will be formed, or otherwise the amount of ammonia will be less. Now, we have to now remember Le Chatelier, who says when a reaction is at equilibrium, whatever we do, the equilibrium does the opposite. So, if I increase the temperature, equilibrium goes in that direction to decrease the temperature. So, here we will see this is an exothermic reaction. So, the reaction gives out heat. That means to bring the equilibrium to favor the exothermic reaction, I have to lower the temperature. So, the conditions are low temperature should be provided. So, low temperature will enhance the exothermic reaction or favor the exothermic reaction, we get more amount of ammonia. But one problem here is, in general, the rates or the speed, ವೇಗ, ಯಾವುದೇ ಒಂದು ರಿಯಾಕ್ಷನಿನ ವೇಗ ಟೆಂಪರೇಚರ್ ಕಡಿಮೆ ಇದ್ದಾಗ ತುಂಬ ಕಡಿಮೆ ಇರುತ್ತೆ. ಸೊ ಈ ರಿಯಾಕ್ಷನ್ ಆದರೂ ಕೂಡ, ಅಮೋನಿಯಾ ಸಿಕ್ಕಿದ್ರೂ ಕೂಡ ಈ ರಿಯಾಕ್ಷನ್ ನಿಧಾನವಾಗಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಇಟ್ಸ್ ವೆರಿ ಟೀಡಿಯಸ್. ಹಾಗಾಗಿ ತುಂಬ ಕಡಿಮೆ ಟೆಂಪರೇಚರನ್ನು ಅಡಾಪ್ಟ್ ಮಾಡುವ ಬದಲು ಬೈ ಟ್ರಯಲ್ ಆ್ಯಂಡ್ ಎರರ್ ಆ್ಯನ್ ಆಪ್ಟಿಮಮ್ ಟೆಂಪರೇಚರ್ ಈಸ್ used here. So, but actually according to Le Chatelier's principle, low temperature favors the reaction. But in this case, we provide around 700 Kelvin to 773 Kelvin temperature, which is medium temperature. In otherwise, the rate of the reaction would be very, very low. Therefore, a 700 Kelvin of optimum temperature is used in this process. Next, coming to pressure. You can see there are 3 plus 1, 4 moles of gases here and 2 moles of gases on the right side. So, what is the effect of pressure? I want the reaction to go where the number of molecules is less, 2. So, I have to apply high pressure so that the equilibrium goes in that direction to decrease the pressure by decreasing the number of moles. And therefore, if I apply very high pressure, equilibrium will go in the forward direction, and therefore I have to apply very high pressure. So, of course, a high pressure which can be borne by the appliances around 20 into 10 to the power 5 Pascal, or this is also called 20 megapascal or 200 atmosphere pressure. A very high pressure is used in this method. Next, You know about some chemical substances which increase the rates of reactions which are taking place very slowly. They are called catalysts. So, we are making use of a catalyst here which increases the rate of the reaction, that is iron oxide. Fe2O3 is the catalyst used which increases the rate of the reaction, along with some substances called, normally we call them as promoters, which enhance the efficiency of the catalyst, and it is a mixture of Al2O3 and K2O. Aluminium oxide and potassium oxide mixture promotes the activity of the iron catalyst. So, with these conditions, we mix nitrogen and hydrogen. So, 700 Kelvin temperature, 200 atmosphere pressure, or you can write this at the bottom also, no problem. Or I can write iron oxide catalyst along with the alumina and K2O mixture, 700 to 770 Kelvin temperature and 200 atmosphere pressure. When applied, nitrogen and hydrogen combine to give ammonia gas. Now we will see the chart, flow chart for the manufacture of ammonia by Haber's process. So, there are two tubes for the nitrogen and hydrogen inlet. So, these two gases are passed to a tank called compressor, where these two gases are compressed to high pressure of 20 megapascal. They are compressed, and then from the compressor they are moving to a chamber called catalytic chamber. This is called catalytic chamber, where the catalyst is maintained in shells. In the shells the catalyst is maintained, and the temperature is also initially maintained to 700 Kelvin, but once the reaction begins, the temperature itself is given out, the temperature is maintained by the exothermic reaction. So, here iron oxide and alumina K2O mixture is kept. So, this is a catalytic chamber. When the nitrogen and hydrogen are entering under very high pressure in this chamber, the reaction begins and ammonia is formed, only maybe up to 15 to 20%, not more than that, because it is a reversible reaction. So, once ammonia is formed in small quantity, maybe around 20%, the ammonia, nitrogen, hydrogen and ammonia are allowed to pass through another chamber called as cooling chamber, where the pipe carrying these gases is cooled. So, in the cooling chamber, these three gases, nitrogen, unreacted nitrogen, hydrogen and the formed ammonia, are cooled in a chamber where ammonia liquefies at minus 33.3 degrees, and you can tap it off from here. So, this is liquid ammonia collected after liquefaction. Now, what about the nitrogen and hydrogen which are unreacted? So, they are not liquefied now, they are passed into this compressor, or directly you can pass them into catalytic chamber or compressor from this, or you can directly pass them to catalytic chamber also. And to bring these two gases, you have to use a pump. So, if you pass it to compressor, again the pressure will be increased. So, nitrogen and hydrogen in 1:3 ratio by volume are passed into a compressor where the gases are pressed or compressed to 20 megapascal pressure and or 200 atmosphere, and under pressure these gases are made to enter the catalytic chamber, where iron oxide along with the mixture of these two oxides is kept in shells, and the temperature is maintained at 700 Kelvin. The reaction begins and ammonia is formed. Ammonia along with the unreacted nitrogen and hydrogen is passed into cooling chamber, when ammonia starts liquefying at minus 33.3 degree centigrade, and the unreacted nitrogen and hydrogen are pumped back into compressor, or they can directly be sent to iron oxide catalytic chamber also. Though this is the flow chart for Haber's process. I think you have got the points now. Now next is properties of ammonia. First we will see ammonia is a colorless gas with the pungent smell. It's highly soluble in water, very highly soluble in water. Now coming to the structure of ammonia, you have studied in VSEPR theory the structure of ammonia, where the nitrogen is sp3 hybridized. It has 4 hybrid orbitals containing single electrons, out of which 3 orbitals overlap with the hydrogen atoms, s orbital of the hydrogen atom, and the 4th one has a lone pair of electrons. Actually the expected structure is tetrahedral with bond angle 109.5 degree, whereas according to VSEPR theory, the repulsions exerted by the lone pair on the bond pairs decreases the bond angle to 107.8 degree, and the structure is called trigonal pyramidal. The structure is trigonal pyramidal with the lone nitrogen at the apex of the pyramid with the lone pair of electron in its one of the hybrid orbitals. So this is the structure of ammonia. Next we will see some of the chemical properties of ammonia. In the chemical properties, it is highly soluble in water. So basic nature I can call it as. So ammonia gas when passed into water dissolves to give ammonium ion and hydroxide ion. Ammonium and hydroxide, and therefore the solution is basic in nature. But the base dissociation constant Kb, dissociation constant of the base is very low, means the dissociation process here is very partial, and therefore it is a weak base. Ammonium hydroxide does not dissociate completely, so it is a weak base. So ammonium hydroxide combines with acids. For example, when it combines with the hydrochloric acid, it gives salts called ammonium chloride, or when it reacts with sulfuric acid, the salts formed are ammonium hydrogen sulfate or ammonium sulfate. When it reacts with the nitric acid, the salts produced are ammonium nitrate. So chlorides, sulfates and nitrates of ammonium are the salts formed when ammonia or ammonium hydroxide, ammonia in water, react with these acids. That is about the basic nature of ammonia. In this case, I wanted to tell you one thing. Ammonia, because of the small size of nitrogen, the electron pairs are attracted towards nitrogen, and nitrogen develops a partial negative charge, and hydrogen starts getting partial positive charge, and therefore these molecules attract each other, forming intermolecular hydrogen bonding. So this will be attracted by some other nitrogen. So the ammonia molecules, due to the compact size or small size of nitrogen and highly electronegative character, the electron pairs are attracted towards it and the bonds get polarized, and due to which this hydrogen and the nitrogen of the other element attract each other, and therefore there is intermolecular hydrogen bonding, and therefore ammonia has a very high boiling point compared to the other hydrides of the family, where these atoms, when you move down from phosphorus to bismuth, are bigger in size, are not able to polarize the bond between hydrogen atoms, and they cannot form hydrogen bonding. So therefore in the group, ammonia has very high boiling point due to intermolecular hydrogen bonding. Next we will see the second property with some salt solutions. When ammonium hydroxide is added to some of the salt solutions like ferric chloride, zinc sulfate or magnesium salts, aluminium salts, their hydroxides are precipitated. For example, you take ferric chloride aqueous solution plus to this ammonium hydroxide is added, then we get a brown, first ferric hydroxide is formed, which then gets hydrated to form hydrated ferric oxide. This is brown precipitate. So ferric chloride gives a brown precipitate of hydrated ferric oxide formed when ammonium hydroxide is added. In the same way, if you take zinc sulfate solution and add ammonium hydroxide, it gives a white precipitate of zinc hydroxide along with the formation of ammonium sulfate. So when zinc sulfate salt solution is added with ammonium hydroxide, we get a white precipitate of zinc hydroxide. So this is how some of the metal can be precipitated as their hydroxides when their salt solutions are added with the ammonium hydroxide. Next, ammonia is a Lewis base. The third property is basic nature of ammonia, where it is a Lewis base. You have studied about Lewis acid base theory last year. A substance which can donate an electron pair is called a Lewis base. So ammonia in its structure has a lone pair of electron which can be donated to other substances which can receive the electron, Lewis acids. Especially ammonia can donate its electron pairs to certain metal ions to form some colored changes which can be easily observed, so that these reactions will help to, you need not write this, help to identify these radicals. For example, a solution containing copper 2+ ions, when mixed with ammonia in aqueous medium, of course, these ammonias will donate electron pairs to copper, the vacant orbitals of copper, and form coordinate bonds. These are donated to copper 2+. So 4 ammonia molecules from 4 sides donate electron pairs to copper 2+, thus forming coordinate bonds, and these such compounds are called complex compounds, and this is blue in color, and this becomes very nice deep blue solution. So with this formation or transition from this color to this color, we can identify the copper 2+ radical. And one more reaction is, when you add silver nitrate solution to any chloride solution or a solution having chloride radical, you get a curdy white precipitate of silver chloride, which you have done in the detection of chloride radical, confirmatory test, silver nitrate test. Silver nitrate is added to any chloride solution, you get a curdy white precipitate. And then in the second column you have written the curdy white precipitate is soluble in ammonium hydroxide. So what's happening here? This silver chloride, when you add ammonium hydroxide, dissolves to give diamine silver chloride and of course water too. So the curdy white precipitate dissolves in ammonium hydroxide to give diamine silver chloride. So this is one more reaction. So we can use this reaction also. The white precipitate becomes a colorless solution. So this is also used in the identification of chloride radical in the laboratory during its confirmatory test with the silver nitrate solution. So ammonium hydroxide or ammonia solution can be used in the identification of the metal or few radicals in the qualitative analysis by observing the color changes or the visible changes occurring in the test tube. So these are about some of the reactions of ammonia. Then what are the uses of ammonia? The uses of ammonia, mainly ammonia is used in the preparation of fertilizers like ammonium sulfate, ammonium phosphate, ammonium nitrate, urea. So these are the fertilizers prepared starting from ammonia. Then ammonia is also used in the preparation of many nitrogen compounds, mainly nitric acid can be prepared starting from ammonia as one of the reactants. Then liquid ammonia is used as a refrigerant due to high enthalpy of vaporization. When it vaporizes, it takes out lot of heat from the surroundings and surroundings get cooled. On repeating this method, the surrounding can be cooled to very low temperature. Therefore, liquid ammonia acts as a refrigerant. So this is all about ammonia, its preparation and properties, uses. Next we will take another compound of nitrogen, that is nitric acid. One more compound of nitrogen we are going to study, the preparation, properties and uses of nitric acid, which is one of the important acids used in the laboratory and some of the industries. Nitrogen forms many oxo acids like hyponitrous acid, nitrous acid, nitric acid, out of which we will study only the preparation, properties and uses of nitric acid. How do we prepare nitric acid in the laboratory? Laboratory preparation. When nitrate salts like sodium nitrate or potassium nitrate, so nitrate salts when are treated with the sulfuric acid, we can write nitric acid and so nitric acid is formed in double decomposition reaction where sodium is replaced by the hydrogen atom. So we get nitric acid formed in when nitrate salts are mixed with the sulfuric acid. So this is how we can prepare nitric acid in the laboratory. The next, manufacture of nitric acid in industries in large scale is very important method in the preparation of nitric acid as well as for your exams. So this is another very frequently asked question, how do you prepare nitric acid by Ostwald's process? So the manufacture of nitric acid by Oswald's process is an important preparation method. So there are 3 steps in the manufacture of nitric acid. So which is the first step? The first step is oxidation of ammonia NH3 into NO, that is nitric oxide. So this is the first step. Ammonia is oxidized into nitric oxide. So what is the reaction? Ammonia plus so you can remember balancing the equation, the numbers 45 and 46. That's why normally the students remember this. 4, 5, 45, 4, 6. So the ammonia molecules get oxidized to nitric oxide. And in this reaction also we have to have such conditions which give you maximum amount of nitric oxide. That is, we use platinum rhodium gauze as catalyst. Platinum and rhodium are made into gauze, like wire gauze, and around 500 Kelvin temperature is used and 9 bar is the pressure. So under these conditions maximum amount of nitric oxide can be produced. So the first step is oxidation of ammonia into nitric oxide. Which is the second step? Oxidation of NO into nitrogen dioxide, NO2. Nitric oxide into nitrogen dioxide. So this is nitric oxide, nitrogen dioxide. So 2NO plus O2 gives 2NO2. So this is oxidation to give nitrogen dioxide. Next, dissolving nitrogen dioxide in water will give you nitric acid. So the nitrogen dioxide dissolves in water to give nitric acid. So these are the 3 very important steps involved in Oswald's process of conversion of ammonia into nitric acid. So here NO is formed, nitric oxide is formed, which is recycled to the second step. So when NO is needed in the second step, so we can use this nitric oxide for the oxidation purpose we can send it to the second chamber of oxidation. Then the nitric acid formed is dilute, which can be concentrated up to 68% by fractional distillation. The water can be removed by fractional distillation up to 68%. Further concentration is not possible and by fractional distillation, and therefore by using concentrated sulfuric acid, which is a dehydrating agent, the remaining water can be removed and we can get up to 98% of nitric acid. So nitric acid around 98% can be obtained by using concentrated sulfuric acid as a drying agent for 68% nitric acid produced. So these are the 3 important steps used in the preparation of nitric acid by Oswald's process. You will have to remember, you have to study, write these equations 5 times, 6 times till you remember all these numbers and values. Next we will see some of the properties of nitric acid. Nitric acid is a colorless liquid. gets a slightly yellow color. When it is exposed to air, by the decomposition it gives NO2, which dissolves in acid to give light brown yellow color. And then around the laboratory purpose nitric acid is around 68%, and in the gaseous state it has structure like this in the gaseous state. And then coming to the chemical properties of nitric acid. Being an acid, acidic property, one is acidic property. It dissociates to give NO3 minus ions, and it is a strong acid giving a lot of amount of nitrate ions. And the HNO3 reacts with the bases to give nitrate salts. The salts of nitric acids are called nitrates. The salts of nitric acid are called nitrates. Next, nitric acid also reacts with most of the compounds. It reacts with the metals and non-metals by oxidizing them into nitrates, and it itself gets reduced to either nitric oxide or nitrogen dioxide or nitrous oxide. So, the second property is action on metals. So, the products formed in this reaction depends on three factors. One, nature of the metal. If you use different metals with the same nitric acid, the products will be different. So, nature of the metal, concentration of the acid, dilute or concentrated acids will give you different products, and then of course is the temperature. So, the products of these reactions between metal and the nitric acid are different under different conditions. So, first we will see the metals like copper, zinc, how do they react. So, metal copper, when added to nitric acid which is dilute, when it is added to dilute nitric acid, it gives copper nitrate plus nitric oxide and water. So, you have 8 HNO3, so 4 water. So, copper when mixed with the dilute nitric acid, it gives copper nitrate and nitric oxide as the product. Whereas, copper when heated with the concentrated nitric acid, look at the condition, this is dilute and this is concentrated with the same metal, it will give same copper nitrate, nitrogen dioxide and water. So, the gas is NO2. The other two products are same. So, concentrated nitric acid will give you NO2 on heating, whereas the dilute nitric acid will give you nitric oxide. In the same way, we can see this is the reaction of copper. How does zinc react with nitric acid under different conditions? When zinc is made to react with dilute nitric acid, it gives zinc nitrate and then a gas called nitrous oxide, and here you can see the product is N2O, not NO like copper when reacts with nitric acid it's NO, but zinc when reacts with dilute nitric acid the product is N2O, and what is N2O? It is nothing but laughing gas, nitrous oxide. So, it is balanced. Okay. So, but the reaction of zinc with the concentrated nitric acid is very much similar to copper. So, it gives zinc nitrate nitrogen dioxide and water. So zinc with the concentrated nitric acid, the behavior is same. So this is how these two metals react with the nitric acid in two different conditions, and the products you can see are different. Now nitric acid doesn't oxidize or it doesn't react with noble metals like gold, platinum, etc. Whereas if you consider the metals like aluminium or aluminium is actually highly electropositive element, should be able to react with nitric acid concentrated. But when aluminium is mixed with the concentrated nitric acid, there is no reaction, or even chromium has no reaction with concentrated nitric acid. What is the reason? The reason is when aluminium or chromium are added to nitric acid, on their surface a stable layer of their oxide is formed, aluminium oxide or chromium oxide, which prevents the further contact between the metal and the nitric acid. So this is called passivity, the active metals becoming passive in concentrated nitric acid due to the formation of a stable metal oxide layer on their surface. Then the third reaction is action on some non-metals. When the iodine or carbon etc. are made to react with the nitric acid, when iodine reacts with nitric acid, it gives iodic acid with the formation of 2 iodic acid, 10 NO2 and 4 H2O. So iodine reacts with nitric acid and gives iodic acid with the formation of nitrogen dioxide and water. Then carbon reacts with nitric acid to give carbon dioxide, nitrogen dioxide and water. And sulfur gets oxidized to sulfuric acid and phosphorus gets oxidized to phosphoric acid. Sulfur, we will see the reaction S8 plus 48 HNO3 will give 8 H2SO4 plus 48 NO2 plus 16 H2O. So sulfur gets oxidized to sulfuric acid and phosphorus gets oxidized to phosphoric acid. So these are some of the reactions of nitric acid concentrated with the non-metals like iodine, carbon, sulfur or phosphorus. Iodine forms iodic acid, carbon is oxidized to carbon dioxide, sulfur to sulfuric acid and phosphorus to phosphoric acid. So next we will see the brown ring test, if you remember, which you have conducted for the conformation of nitrate radical in the laboratory. So the nitrate radical solution, the salt solution containing nitrate is prepared, which is then mixed with the ferrous sulfate, freshly prepared ferrous sulfate solution, to which we add concentrated sulfuric acid very carefully through the sides of the test tube. And in the side of the test tube, when the two sulfuric acid comes down being heavier, when the two meet, you see a brown ring. So a brown ring is formed at the junction of two liquids. What is happening here? This is called brown ring test. Here the ferrous ions get oxidized to ferric ions and reduce the nitrate ions into nitric oxide. Nitrate ions are reduced in acid medium. In the acid medium, nitrate ions are reduced to nitric oxide and ferrous gets oxidized to ferric. Then the nitric oxide reacts with the ferrous ions to give a complex which has brown color. Nitrosyl compound of ferrous ion one H2O goes out, NO comes in and one H2O molecule goes out, and this is responsible for the brown color formed in the brown ring test. So this is about all the reactions of nitric acid. Then what are the uses of nitric acid? Nitric acid is used in the manufacture of urea, or it is used in the manufacture of ammonium nitrate, superphosphate of lime, all these fertilizers. Nitric acid is used in the preparation of TNT, trinitrotoluene, or TNG, which are used as explosives. Nitric acid along with sulfuric acid or alone in the fuming state is used in the nitration of organic compounds, and it is also used in pickling stainless steel, the surface to be clean, or etching of metals in the metals to make some designs, and as an oxidizer in the rocket fuels. These are the uses of nitric acid. We have studied about group 15 elements, then about preparation properties and uses of nitrogen, ammonia and nitric acid till now. With this, the study of group 15 is over. Next, we are going to start group 16 elements. So, you can see group 16 after the group 15 in the periodic table at the right extreme end, group 16 elements. First, we will see which are the elements present in group 16 are oxygen, then sulfur, selenium Se, and tellurium is Te, and last one is polonium PO. So, these are the elements present in the group 16. And now we will see the occurrence. Where do we get these elements in nature? So, we will start with the occurrence, and then we will study their atomic properties and the variation trends in the group, and then physical properties, then chemical properties, and then anomalous behavior of oxygen, as you have studied in group 15 for nitrogen. So, then some few compounds of oxygen and sulfur we are going to study in group 16. To start with, occurrence of oxygen. You know very well in the Earth's crust there is abundant element with 46.6% by mass of Earth's crust is oxygen. So, the most abundant, it is present as minerals mainly in the form of silicates, oxides, carbonates, sulfates, etc. And in the air we have 20.946% by volume of air contains oxygen is present in the air to the percentage of 20.946 by volume. That is about oxygen. The next one is sulfur. Mainly the sulfur is present in the form of sulfate minerals, sulfides, and also there are other forms of sulfur we will see later. So, sulfate, sulfur occurs in the Earth's crust in the form of sulfates. For example, one important one is gypsum with the formula CaSO4 2H2O. Then one more is Epsom salt with the formula magnesium sulfate 7H2O, and barite is a sulfate of barium BaSO4. So, these three forms of sulfates of different metals are examples for ores or minerals of sulfur in the form of sulfates. Then it is also present in the form of sulfide minerals. Sulfur is also mainly present in the earth's crust in the form of sulfide minerals. For example, sulfides are zinc sulfide called as zinc blend, lead sulfide called as galena, CuFeS2 called as copper pyrites. Not only this, in volcanoes and the exhaust gases also hydrogen sulfide is present in some countries, and sulfur is also present in some organic matters or compounds in the form of different sulfur compounds. Mustard, garlic, onion, eggs, hair, wool, etc. also contain sulfur in the form of different compounds. Then coming to selenium and tellurium. Selenium and tellurium are present as their, like sulfur as sulfides, oxygen as oxides. In the same way, selenium and tellurium are present as selenides and tellurides in the earth's crust along with some sulfide ores. Then polonium is the metal which is radioactive and is present as or obtained as the decay product of uranium or thorium minerals. So polonium is radioactive, short-lived with 13.8 days of half-life period. So this is about the occurrence of these elements in the nature. Then we will see some atomic properties as we have done with the group 15 elements. Electronic configuration. As you know, there are 6 electrons in the outermost shell and the outermost electronic configuration in the outermost shell, that is Ns2 Np4. There are 6 electrons, 2 in the first Ns and 4 here, and there is 1 lone pair and there is another. There are 2 lone pairs in oxygen atom and 2 unpaired electrons in the p orbital according to Hund's rule. Now, oxygen with atomic number 8, it is 2s2 2p4. Next neon is 3s2 3p4. After argon, selenium is 3d10 4s2 4p4. Krypton, tellurium after krypton is 4d10 5s2 5p4, and polonium with the xenon 4f14 5d10 6s2 6p4. So you can see all these have similar outer electronic configuration and therefore their properties are expected to be the same. So this is atomic number 8, this is 16, 34, 52 and 84. Then we will study some of the atomic properties. First we will see atomic radii after electronic configuration. The second one is atomic radius. You know very well, as I have told you in the group 15 elements, with the addition of new shells, the atomic radius goes on increasing as you move down. So when you come down, the atomic radii increases. And then we will see the ionization enthalpy. When you move down, once again with the increase of the size, removal of the electron becomes easier and ionization energy decreases with the increase in the size. Next we will have another property called electron gain enthalpy. Electron gain enthalpy. So when you come down, the capacity of these atoms to gain electrons decreases due to the increase in the size. Therefore, the electron gain enthalpy becomes less negative. So, lesser energy is given out. So, it becomes less negative. So oxygen is expected to have the highest negative electron gain enthalpy, and there onwards the value becomes more and lesser negative. But the problem here is oxygen has lesser negative or less negative electron gain enthalpy than sulfur. So the electron gain enthalpy of oxygen is lesser than that of sulfur, which is expected to be otherwise. That is due to the small size of the oxygen atom. The inter-electronic repulsions do not allow the easy addition of another electron, and therefore oxygen, even though highly electronegative, it needs electron, but the space is very less and the already present electrons repel. So ಸಣ್ಣ ಸೈಜಿನಿಂದಾಗಿ ಆಕ್ಸಿಜನ್ ಆಟಮ್ನಲ್ಲಿ ಅದಕ್ಕೆ ಎಲೆಕ್ಟ್ರಾನ್ಗಳನ್ನು ತಗೊಳ್ಳುವ ಆಸೆ ಇದ್ದರೂ ಕೂಡ ಹೊಸ ಎಲೆಕ್ಟ್ರಾನ್ ಎಡಿಷನ್ ಆದಾಗ ಅಲ್ಲಿ ಸಣ್ಣ ಜಾಗದಲ್ಲಿರುವ ಮೊದಲೇನ ಇರುವ ಎಲೆಕ್ಟ್ರಾನ್ಗಳು ವಿಕರ್ಷಣೆಯನ್ನು ಮಾಡುವುದರಿಂದ ಅದರ ಎಲೆಕ್ಟ್ರಾನ್ gain enthalpy is less negative than sulfur. Okay, this is then coming to electronegativity. Of course, due to small size, oxygen is highly electronegative. It is after fluorine, so the value is 3.5 given in Pauling scale. So this is highly electronegative. With the increase in the size, electronegativity goes on decreasing, and therefore all these properties affect all the natures of these, and therefore oxygen and sulfur too are non-metals. The next two are metalloids. Due to the decrease in the ionization energy, this is a metal. So all these properties are reflected in the metallic and non-metallic characters also, and therefore with the decrease in the ionization energy, with the increase in the size and increase in the electronegative values, oxygen and sulfur are non-metals, and selenium and tellurium are metalloids, and polonium is a metal. Now about the physical properties, we will see the physical properties of these. Oxygen is a gas and all the others are solids. Oxygen is a gas, all the others are solids. Oxygen is a gas and others are solids. And then I have already told you these two are non-metals, metalloids, and this is a metal. All these elements exhibit allotropy. All these exhibit allotropy. And as usual, with the increase in the number of electrons, atomic mass or molecular mass, the melting point and boiling point of these elements increases as you move down. There is a large difference in the melting points of oxygen and sulfur. A large difference in the melting point is observed, which is not observed in the other cases in the trends. That is attributed to the atomicity. Here oxygen is only diatomic, easier for melting, but sulfur 8 needs very high temperature to melt because the atomicity of sulfur is S8. So these are some of the atomic properties and their trends. So with this, students, I'll conclude this session, and the remaining chemical properties and the remaining concepts to be studied in group 16, I will continue in the next class. Thank you. Take care.